What's up, guys? Today we are going to talk about a question that deals with two different sections. One section in which you're experiencing some acceleration, which is change in velocity, and then another section in which you're not experiencing any acceleration, so your velocity is going to be constant. And then we're asked in this question, well, let's just read it together. Since raindrops grow as they fall, which is cool on its own, by the way, their surface area increases and therefore their resistance to their falling increases. A raindrop has an initial downward velocity of 10 meters per second, and its downward acceleration is this following stuff. So you can see for the first 10 seconds, it's experiencing this type of acceleration. And if we just take a second to look at it, when t is 0, it's going to be 9 minus 0. So acceleration starts at 9 meters per second. And then as t increases, you're taking off more and more, up until t is equal to 10, in which case you're taking off a full 9, which is why it's then 0 after that. Okay? If the raindrop is initially 500 meters above the ground, how long does it take in seconds to fall? Okay, so we should consider breaking this problem down into two distinct sections. We talked about that. The second section will consider everything that happens after acceleration stops, which we know is 10 seconds after the raindrop starts to fall. This might be a good idea since we have no other way to deal with motion equations that have multiple formulas for acceleration. We've seen other problems that have acceleration that's changing, like in this case here, so non-constant acceleration, but not ones that have two different sections. So we don't have an equation that just brings everything together. But that's fine. We can just do it separately and then use logic to piece it together. Section 1, the first thing I'd like to know is how far the raindrop fell in the first 10 seconds. That would be wonderful information to have, so that's what we're going to try and piece together. Only problem is that I don't have a position function. Fuck balls. Okay, well, I have an acceleration equation, so I'll be able to construct a velocity equation. Let's start with that. So what's a velocity equation at some arbitrary time t? Well, it stands to reason that it's equal to the initial velocity plus the sum of all the little itty-bitty changes to the velocity in the first t seconds. Right? That makes sense. So the final velocity is the initial velocity plus all the changes to velocity that you've experienced. But acceleration is changes to velocity, right? The units are meters per second per second. So how many meters per second do you change every second? That's exactly what acceleration is. So the sum of all the little itty-bitty changes to velocity in the first 2 seconds is this integral. That's what integrals are really good at doing. They're really good at adding up an infinite amount of things, and you want to add up all the changes to velocity, which is acceleration. See how much sense that makes? It's wonderful. Okay, so what do we know? Well, we're only interested in the first 10 seconds or things that happen in the first 10 seconds. So this acceleration equation is this top one. So we can just replace it right there. Boom. Okay, now, where did this come from? Well, I took an antiderivative, didn't I? Took an antiderivative of 9 minus 0.9 t. Why did I do that? I did that because Newton's badass and he discovered the fundamental theorem of calculus. And so instead of using Riemann sums, I can just use antiderivatives. So I do. And then I'm supposed to put in t and 0. So I listen to Newton, he's a smart guy. I put in t, here we go, and then I put in 0. These guys all go away. See you later. And this here is my velocity function at some arbitrary time t, as long as t is within this time frame of 0 to 10 seconds. Okay, awesome. Now we can use this equation to construct a position equation. All right, let's do that. So what's position at some time t? Position at some time t is given by, well, my initial position plus the sum of all the infinite little itty-bitty changes to position. Makes sense. Oh, but wait, that's just the integral of velocity, because velocity is change of position. So we want to add up all the little changes of position. That's the same thing as taking the integral, in this case, up to our point t of all the changes in position. So we do that. Now that we have a velocity equation, we just pop it in there, and then we do the same thing again. This is due to fundamental theorem of calculus. That's right. We plug in t, we plug in 0. The zeros all go away. See you later. Thanks for coming out. The initial position I'm going to set to 0, and then you can do this a few different ways. Like you can set it to like -500, and then you'll get to like -400 or something like that. Anyway, I set the initial position to 0. And that works out fine in this case. So we're going to see how far we fell in that 10 seconds. So just keep in mind that, you may see other solutions to this, and it's totally fine. As long as you end up with the same answer, you're totally good. So simplify, blah, blah, blah. Okay, sweet. Well, now we can check and see how far we got in the first 10 seconds by plugging in t equals 10. We have a position equation. We just plug in the different times we're interested in. We're only really interested in at the end, at 10 seconds. So I plug it directly in there, S at 10, and I get all this mumbo jumbo. You guys can simplify that whichever way you want, and you get 400. Awesome. That means that in the first 10 seconds of free fall, this dope little raindrop fell 400 meters. Great job, little buddy. There's 100 meters to go. And now we're going at constant velocity since acceleration has ceased. Okay. We've already found an equation for velocity, so let's use that to see how fast little drop was going when t equals 10. So we're accelerating. We got to 400 meters, and then at that time, which is time equals 10, we stopped accelerating. And now we're going our constant velocity. It's going to stay the same until we hit the ground. I'd really like to know what that velocity is, because then I can use that to find out how much time it takes to fall that remaining 100 meters. Okay, so this is our velocity equation that we solved for before. Let's find out what the velocity is after the 10 second, because that's going to be our final velocity. And we just plug in, do some mumbo jumbo here. I don't even know how to do these calculations, no idea. V10 is equal to 55. Awesome. So that's meters per second. At this point, the hard work is done. We've got 100 meters to go, and we're traveling at a constant 55 meters per second. We want to know how many times 55 will go into 100 since each time it does, it represents a second of travel time. Okay, isn't that cool? If you had 55 meters to go and you're going 55 meters per second, obviously that's 1 second. If you had 110 meters to go and you're going 55 meters per second, since every time 55 goes into 110 represents a full second, then that's 2 seconds of travel time. That's why, among other ways, it makes sense to take your total distance and divide it by your speed to output time. Okay? So that's all I do here. We just do 100 divided by 55. 100 is the remaining distance. 55 is the final speed. And if you simplify that, you can divide by 5 on top and bottom. You get 20 over 11, which no longer simplifies. So how long was the whole trip? Because that's really what they're interested in. If the raindrop is initially blah, 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 how long does it take in seconds to fall the full 500 meters? For that, we need to add up the total time it took for the first section to complete and then the total time for the second section. First section total travel time, 10 seconds. They just tell us that. The whole question was finding the second travel time, which is 20 over 11 seconds. Not quite 2 seconds, more than 1. Add those puppies together and that'll give you your answer. I hope this explanation helps. As always, let me know if you want me to do any other questions. Head over to the Facebook group, whatever, email me, whatever. And good luck with this stuff. We'll talk to you guys later. Cheers.